Hello, it's Jonny here, the founder of The Data Scientists, a company in Porto, in Portugal. And I want to talk to you today about a topic that I've become quite interested in, and that is the mathematics of AI and machine learning. I know that sounds a bit scary, but let's get into it. I think I'll try and make it as interesting as possible. You can see that I am not young. I have got lots of grey hairs. I'm in my 60s now, and machine learning and AI is just a dream. It could not have really, we couldn't have imagined it when we were kids. And when I first saw it, I thought, wow, what kind of mathematics is there behind this? The reason for that is well, AI kind of taken me by surprise. I just didn't think that it was something that would be possible in my lifetime. And I am passionate about mathematics, studied mathematics at school. I went on to study mathematics at university, a topic I use every day in my daily work with the data scientists here at JTA. But the surprise when I started looking into this is that I found that the concepts that are used are really quite simple. And I want to sort of talk to you about that and give a bit of an understanding. And the other thing that fascinated me is the history. I want to talk about the history of this kind of mathematics. It dates back thousands of years, and so I think that's really quite interesting, and I sort of wanted to touch on that during this series. Just to put your mind at rest, I only will use high school mathematics, and it's hopefully be quite easy to follow. So it should be fun and visual and not lots of mathematics. So I wanted to start with, I was thinking, well, what was really one of my first if you like, examples, my first introduction to machine learning. And when I thought about it, what came to mind was this. This is a high school calculator, a Casio FX39. And I would have got something like this. This wasn't the actual one, but when I was probably about 13, 1977, somewhere like that. And all the kids would have had these sort of things. When I first got it, it was confusing to me because it's got things written on it: ln, log, sin, cos, tan, hip, or is it hype? I didn't know, but I was fascinated to learn more about it. But of course, even though I didn't know what those things did, I would just play with it and I'd jab away at buttons. And there was one button that I found really quite fascinating. Anyway, I'll sort of show you that. I happen to have a camera here by my side that I can kind of give you a close-up. So let's kind of move over. Here's my kind of work desk. I'm here. And there it is, the trusty Casio FX39. Absolutely wonderful. And yeah, as I said, I used to sort of press buttons and, oh, there's one, it's giving me an error. E, that's not very encouraging. That's giving me a 0. Oh dear, that's rather boring. What about sin? Or what's its sign? Oh, that's really rather boring. So different things kind of happen. Oh, another error. There's one button that I used to find fascinating, cosine. And I hit that button, it gives me a number 1. I'm going to hit it again. Ooh, a whole stream of numbers. What is that number? Now when I hit it again, I've got a whole stream of different digits, and different digits, and different digits, and different digits. And it just keeps on going. And one of the things that was kind of interesting, we started off with 0, but I suppose if I start somewhere like 5 and I press a button, it's giving me different digits. But I soon discovered an interesting fact. If you keep pressing this button, it actually gets you to a number that doesn't move. And it doesn't matter if you start at 0 and jab the button, or you start at 5 and jab the button. If you jab it enough times, you will get to a number that it's the same number. So I was thinking, well, what is going on there? what is all of that about? Anyway, so let's look into that. I think it's actually quite interesting. I'm going to use a little tool that is available on the internet. It's a website and it's called Desmos. It's a mathematical calculator. It's a wonderful thing. Allows you to sort of just play and experiment. And so I'll show you my Desmos screen. So it looks like this. I've got, that's my screen. I put it into full screen mode. There's a green wiggly line. That is the graph of y equals cosine x. And then the purple line is actually y equals x. Actually, I am lying. I have a little mechanism in Desmos which allows me to scale my line. There you go. That's correct now. That is y equals cosine x. I'll come on to explain why I want to bunch that up and why I want to do that later on. And one of the things here is, you know, you can see that I can change where I can move my my starting point. So without further ado, what I'm going to do is I'll come back into the picture and I'll explain what it is I'm using Desmos to do. So over here are the definitions, and I've got here a function which is cosine of, ignore the phi for a moment, function 1. And down here I've said the function at n minus 1, if you apply a cosine, becomes the function at n. This is the way I tell Desmos to just keep repeating the function. And what I've asked it to do is apply f1, which is a cosine. So what this is a way of sort of, in a kind of mathematical terminology, of just repeating that function again and again. And what I can do is, by moving this slider, Desmos actually calculates the numbers. And let me explain why I'm seeing these lines. So we start off with 0. And if you remember, when I hit the cosine button, of course, the cosine of 0 is 1. But a calculator doesn't have an x-axis or a y-axis. It has a screen. So when I hit the cosine again, it basically takes this 1, but it's an input this time. So the 1, if I move across this to this line, which is y equals x, basically that's where we would get our 1. And then we find out what the cosine is again. I think that was our 0.54, if I remember rightly. And we can go to y equals x, so that's where the number would appear on our screen. And then we try again, and bang, it gave us a 0.8. So what this is doing is it's actually showing graphically how the number is evolving on my Casio screen. And what you can see is, it's rather lovely, it's a bit like a black hole. These lines get pulled in. I can zoom in here. They get pulled in like this and fall into this sort of well. And eventually the number that it gives is this point where the two lines meet. Well, as I said to you before, one of the green wiggly one is y equals cosine of x, and the mauve one is y equals x. And so where these two lines meet is x is equal to cosine of x. So what my Casio calculator was doing when I jabbed the buttons like crazy was it was actually giving me the solution of this equation. It's quite a hard equation for a human to solve. There's no nice easy way for us to solve it, but the system has done it, and we're able to sort of see this sort of nice graphical example. And like I said, I was able to move. I started off at 5. Well, you can see here I can actually drag the starting point, and I can change whereabouts I want to start my calculation, and it doesn't really matter where I start. the calculator might be quite a long way from the solution, but it falls into that well and gives me a solution. So that graphically is a sort of picture of showing you what my calculator was doing. Machine learning starts with a guess. We don't know what the answer is. It repeats a process using a machine. It gets to an answer. That is what machine learning is all about. Now, I would occasionally get really wild when I was incredibly bored at school and try something, really quite exciting, like pressing cosine, and then x squared, cosine, x squared. And what happens, and why is this of interest to us? Well, let me show you what happens. What I'm going to do, let's go back to 0, and we'll move our start point back to 0, and I can hide my green wiggly cosine, and this is a graph of what a cosine followed by squared looks like. It's an orange wiggly line. Now, if I want to analyse how this is going to work, I have to tell Desmos to, this is now function 2, so I ask it to do my jabbing, repetitive jabbing now on function 2. And here you can see, we've got a solution. It's where these two lines meet. What do you think will happen? Will it actually find a solution? Well, the answer is yes. It's another kind of well, and look, everything is now sort of going in. But one of the things that I find really interesting is that there's a lot more lines, and the lines are getting closer and closer together, and it needs me to make a lot more jabs before we get close to a solution. In fact, I think now this is, even if I move my slider all the way over, you can see that it's not quite got there because it's slowing down. It's getting closer and closer and closer. So we don't really get to a solution. This one's not working so well. And I think that's quite fascinating. I would then, as an experiment, try something a little bit different, which is, what if, instead of taking cosine x squared, what if I did it the other way round, and I sort of went, well, what's cosine followed by square root? Cosine followed by square root. So I can go back and let me put that chart up, and I need to ask Desmos to do repetitive jabbing on function 3. It's a different shape of function that we see here. It's hard for, you can't define the square root of a negative number. In higher mathematics you can, but at high school maths you can't. And Desmos is respecting that. It's showing me what the square root is of all the positive bits, but it has to ignore the negative bits. And that's quite interesting, because we can sort of look and see, well, what happens when we choose a number that's somewhere different. Now, will this find the solution? There is a solution. There it is. They are kind of, linking up there. And let me see. So, now what's happened there? When I was moving the slider before, we just kept seeing more and more lines. Now, I can't really see any lines being generated. And let me really try and zoom in here. Let's go further and further. Are we seeing more lines? No. And the reason for that is, this is such an attractive point that this well of attraction, the line, basically goes within a few odd iterations there, it's hit the answer. And it found the answer so quickly that all these other new iterations aren't helping at all, because it's already got to the answer. This is a way that my calculator was actually able to find a solution really, really, really quickly. Let me just pull out from here. But the problem with this function, which I think is obvious, is I can move my starting point up to a certain limit. You see, it's still finding the answer. But what if I plonk it here in no man's land? It can't find the solution. But once I move my starting point back over here to where the curve is defined, it works again. So this is an interesting thought, is machine learning. Will there be places where it's actually important, where we start, our starting assumption? Could we have machine learning that sort of finds an answer if we start at the right place, but we don't start at the right place? It won't find an answer. This is actually a real problem in machine learning. The reason why the cosine followed by x squared and the cosine followed by square root behave differently. One's slower than cosine to find a root, and one is much faster, is really down to the slope of and the curvature of the lines where they cross. And I can give a very simple sort of example of this. So I'm going to come back to the beginning. Let's reset. Let's start again at 0. I don't want to show that anymore. I've got another line which I will put up on my, hopefully, here we are. This isn't a curve. This is a parallel line, and it's F4. So let me ask Desmos to have a look at F4. There's nowhere, because these lines are parallel, that they cross and there's a solution. So quite understandably, if I try and ask my calculator to find where they cross, it just disappears off into infinity. It can't find a solution. But if I twist that line round, like there now is a solution. And one of the things that we find is, bingo, the calculator has found the solution again. It's all worked and worked really nicely. So this is just an example trying to illustrate that this slope actually is making a difference. One of the things that's particularly interesting is if I set this slope to -1, what this means is, zoom in again, these cross at right angles. They're straight lines and they cross at right angles. Now when I start, my well starts to get formed and we go round in a square, but the next time it goes round in a square and round in a square and round in a square, and it's not sucking in like that sort of the lines to find the solution where there is a solution. In this case, it's just locked in this sort of, it's in orbit, if you like, and it's not able to sort of find a solution. But if I move the slope slightly, there's an example where it actually needs lots of iterations to find the answer, not so many, not so many, not so many. So we can see how the slope is really sort of, oh, what's happened here? Suddenly, my point, instead of being an attractor and attracting a solution, it's become repulsive. And my solution has gone zooming off into infinity. So if I kind of come out here, you can see that it's just going out, and we're already out around thousands, numbers that are in the thousands. So I think that's really very interesting. My final illustration that I sort of wanted to show you was, I'll hide that, we'll clear that, and I wanted really to come back to my original cosine, and as you saw at the beginning, so there's my cosine, we can't see the wiggly line. Why is that? Because it's so small at this level of zoom. So let me come back in and bring back my wiggly line. And what I can do with this wiggly line is I can stretch it out, and but I want to bunch it in. And the reason why I want to bunch it in is we know that there's a solution here where these two points happen to match. But you see here, it's actually very close. They're getting very, very close down here. And as I bunch this thing in even more, oops, it actually gets to the point where it kind of crosses over. So what we've got here, there's a solution here, there's a solution here, and there's a solution here. 3 solutions. If I kind of continue, you can sort of see that I can bring in other solutions. But let's just go back to where we were, and I want to look at the case where, actually I think I'll set this to a nice round number. Let's set that to 3. There's a solution there, and it looks like there might be a solution there. So what I need to do is just go back to our original cosine function, and we can just start to have a little look and see what happens. Now, oh, it looks like it went and found a solution very, very quickly. But it didn't find this solution, it's gone down to a solution here. But let me move the starting function. Okay, that looks, oh, what's going on here? Suddenly, I'm getting some really wacky behaviour. I mean, look at this one. I find that, you know, really interesting. So the lines are going all over the place. But if I zoom in at this route here, it's like we saw before with that straight line. This is sort of repelling. It tries to find this route, but then the line gets repelled. So, you know, what's that telling us? But then eventually, it looks like the line has gone down here, and I'm probably going to have to really, really zoom in to see what has happened here. Okay, I can see that finally it is, let me see if it will get closer. There you go, look at that, I can just finish it off. That was perfect timing, wasn't it? And it's got to a root. It has found a solution. But in this case, there is a solution here. There's a solution here. There are 2. And then zoom out, and there is also a solution up here. There are, so there's 2, it's hard to see that now, and there's 1 here. There's 3. Why did the system decide to get that route? Why not any of the others? And it's zoomed around and it's tried to get to that route, but it didn't. But is this a stable thing? It doesn't look very stable. If I change the place where I start, it's kind of, you know, sometimes it looks nice, and look at that. It got there beautifully. But then suddenly it gets that one there. It's horrendously complicated, the path that it has to take to find the answer. So all of this is quite interesting because, you know, this is important in machine learning. Machine learning will also, on a bigger scale, you know, proper machine learning, is going to suffer from all of these sort of things. Anyway, so I do hope that you sort of enjoyed some of those examples that we've played with, you know, with Desmos. I think, you know, it's a fascinating tool. I just love playing around with Desmos because you can really sort of look at all sorts of different scenarios and really sort of get a feeling for what's going on. this is important if you want to study machine learning, getting that sort of feeling. Anyway, I'll just wrap up there, I think, and with some key points. What is it that we've sort of learned? I seem to have disappeared. I can bring myself back in. There we go. Some functions naturally behave. We saw that cosine is lovely, it just works. The others sort of didn't. That's not necessarily the norm. That's a learning point. How can we solve iteration problems for a function that isn't well behaved? That's something we're going to come on and look at in podcast number 3 in this series. The cosine function tames a number. This is something we've kind of brushed upon. It goes down to minus infinity. It goes up to plus infinity. But the answer to the cosine will always be between minus 1 and plus 1. And that's actually really useful in machine learning, that some kind of output that could be any kind of weird, wacky number, we can bring it down into a usable range. That is a nice little thing to have in our kit bag, a tool that is going to be useful. We'll talk about that in yet another podcast. And then that final example, there are many solutions. And how do we know which one is the right one? And the whole issue of starting, where do we start from and where do we end up, is something that people who are working on machine learning, they have to grapple with these problems all of the time. So yeah, that's sort of really what I kind of wanted to talk to you about today, and I hope that you enjoyed the podcast, and I'll see you again on the next one, where we're actually going to go back 2,000 years, and we're going to look at some, well, they weren't machines then, but machine learning techniques that were written about in Babylonia in AD 60. And so I hope you enjoy it. See you then.